As we start to talk more specifically about metabolism, we need to talk briefly about bioenergetics, or how energy changes are coupled to chemical reactions. Within any given system, the energy available for doing work is termed Gibbs free energy. And based on the first law of thermodynamics, we know that the energy of a system remains constant, and therefore the energy is not gained or lost during any of these chemical changes. More simply put, the energy before a reaction is equivalent to the energy after a reaction. We also have to consider two other terms to define the second law of thermodynamics, and those are entropy and enthalpy. Entropy is the extent of disorder or randomness of the system and becomes maximum when equilibrium is approached. It can also be defined as order. Low entropy are highly ordered systems, whereas systems with high entropy have a high level of disorder. In contrast, enthalpy is the total heat content of a system. And if we put this in the context of a chemical reaction, these reactions will either require heat energy to move forward, meaning heat energy will need to move into the system, and this will increase enthalpy, or heat will be given off during a reaction, and this will decrease the overall enthalpy. So now let's look at how we use the terms entropy and enthalpy to calculate the free energy of a reaction. This is our equation here, with delta G being Gibbs free energy, delta S being our change in entropy, and delta H being our change in enthalpy. So in solving this equation, what we're most interested in is the sign on delta G. If the delta G is negative, the reaction will proceed spontaneously with a loss of free energy, and this loss of free energy is likely in the form of heat. That's termed an exergonic reaction. Likewise, if that delta G is of a great magnitude, the reaction virtually goes to completion and is essentially irreversible. In contrast, if the delta G is positive, the reaction proceeds only if free energy can be gained. And in that case, the reaction is considered to be endergonic, meaning energy needs to be added. And finally, if delta G is 0, the system is considered to be at equilibrium, and there's no net change in product or reactants taking place. So now let's look more closely at the terms exergonic and endergonic in the context of a reaction scheme. So first, let's look at the reaction from A to B. In this reaction, we'll say the delta G is negative, and it's spontaneous. This reaction would be exergonic, and the reactants A would be at a higher energy state than the products B. Conversely, if we look at the reaction C to D, this is pretty unlikely, as indicated here by this rock. Not much is going to happen to this rock without adding energy to the system. If we look at this in terms of free energy, it's an endergonic reaction. Our reactant C is going to require some energy to get it up to our product D. So in biological systems, what we like to do is couple exergonic reactions with endergonic reactions such that we can use the change in free energy from our exergonic reaction to drive our endergonic reactions. So here you can see if we coupled these two reactions, our product D is still at a lower free energy state than our initial product A. Therefore, this change in energy here would be given off as heat. However, the rest of the free energy given off by the transition from A to B could be used in the reaction to convert C to D. And that is how most of these biological systems will work. So in this case, we could use the energy released in our conversion of A to B to move our rock down the hill to eventually get it to product D. So what we'll see throughout metabolism is that we'll use ATP as an intermediary energy carrier to transfer energy from exergonic reactions to endergonic reactions. There's a significant amount of energy stored within these phosphodiester bonds, and the cleavage of these bonds can donate energy to a reaction, or can transfer a phosphate to a reaction scheme itself. There are three major sources of ATP production that we'll talk about. The first is oxidative phosphorylation, and this is the process by which the oxidation of NADH or FADH2 is used to synthesize ATP in the mitochondria. The next is glycolysis, and there are several ATP produced. And finally, there is one GTP produced directly from the TCA cycle. These are all very important producers of ATP, as there's a significant need for ATP within the cell, as well as free phosphate and ATP intermediates. So again, if we look at our ATP molecule, the high energy is in these phosphodiester bonds, with the most energy being in the hydrolysis of the last phosphate group, so cleavage of this bond here. The energy carried in this bond can then be transferred into a reaction that's endergonic and move the reaction forward. So let's finish our discussion of delta G and energy transfers by looking at this question. So if we look at delta G across a reactant series, we can say that they're additive, meaning that we couple endergonic reactions to exergonic reactions in order to move a reaction series forward. So if we are given the individual delta G's for each of these reactions, can we answer the question as to whether this reaction series is endergonic or exergonic in nature? So first of all, what we need to do is determine whether or not the overall delta G of the reaction series is positive or negative. If you can look here, minus 10 plus minus 1 plus minus 2 leaves us with minus 9. Minus 9, that leaves us with a negative delta G, meaning this reaction is spontaneous. So in that case, this summarized reaction series would be exergonic.